Alright, so the final question, question 88. Give the products of the following reactions, including their configurations. So there are a total of 4, 5, 6, 7 different of these questions, and I'm going to go through 3 of them just to kind of make sure you have an idea of how to approach these problems. And I would really encourage you to go through and do all of the other variations, but if you can do these first 3, you can definitely have a really good idea of how to actually approach doing the other ones. So for each of these, there are a couple of things that you need to consider. One, you always need to consider regiochemistry. So where the reagent is attaching to the alkene, and specifically what part of the reagent is attaching to the alkene. And that's the main bit. After that, since we're now on chapter 5, stereochemistry, you have to start worrying about other things. So this is priority 1, it's the regiochemistry. Priority 2 is always going to be stereochemistry. So these are questions like, is the reagent going to add in an anti fashion? Is it going to add in a syn fashion? And when we say anti or syn, it really depends on the situation. So to go back to the first one, for regiochemistry, what we're really asking is, are we adding Markovnikov or anti-Markovnikov? Those are the two main regiochemical designations, okay? So beyond that, once you move on to stereo, this anti and syn terminology is also kind of thrown around. So it's really important not to get that confused. So you can have reagents adding in an anti-fashion, like this Br2 in DCM, but that has nothing to do with adding anti-Markovnikov, okay? Because we're adding 2 BRs. So because it's symmetrical, there is no technical Markovnikov or anti-Markovnikov. So just keep it in mind that for stereo, we can add syn, we can add anti, or we can do some variation of that. So once you have something that has multiple possibilities, like carbocations, you have to worry about whether something will always add anti, something will always add syn, or whether for the C plus variation, you can get a combination of the 2 different variants, okay? So these are the first 2, or these are the 2 different things you need to make sure you understand beyond just knowing, okay, well, what does this reagent do? That's the main thing before regio and stereo, being able to remember, well, if I add Br2 to the alkene, how is it going to transform the alkene? That's the first bit, really. Okay, so let's just go through these. So for the first variation, Br2 in DCM, well, the DCM you have to recognize is just solvent. So it's not really going to take part in the reaction, it's just something to allow the reaction to go forward. The second thing is that you have to remember that the Br2 addition is, it's neither Markovnikov or anti-Markovnikov. Okay, we're going to add 2 different BRs. One's going to go onto the blue carbon, and one's going to go onto the yellow carbon. So this Markovnikov or anti-Markovnikov designation is really meaningless. So we actually, kind of in a good way, this is kind of meaningless for this Br2 addition. So then we just move on straight to the stereochemical designation. So you have to remember Br2 with DCM is going to be an anti-stereochemical result. So that means that if one Br is facing up, the other is going to be facing down. So this is really important because once you recognize that Br2 adds in an anti-fashion, everything just gets exponentially simpler. So let's just go ahead and draw Br2, or the 2 BRs, added to these yellow and blue carbons in an anti-way. So let's go ahead and do Br2 in an anti-fashion. So here's Br and here's Br. Okay. Now let's pretend that, again, we have to worry about 3-dimensionality. So we can have the Br2 attacking the alkene from above, or we can have the Br2 attacking the alkene from below. So what that means is that if you took this guy, everything is in the plane of the board in this kind of designation, but if you took it and you flipped it along the x-axis just a tiny little bit, you can imagine, if we did this flip along the x-axis like this, and let's just turn it by 90 degrees. So we're just going to turn it by 90 degrees, and in that case we have hydrogen going back and methyl going back, and we still have our double bond, and we now have our isopropyl group coming forward and methyl group coming forward. Okay, so again, remember that these are no longer in the plane of the computer screen, no longer in the plane of your paper. This is actually saying these H and ME groups are going away from you, and these are 3D coming at you as if you're watching some kind of 3D IMAX something or other. Okay, so at this point we have two different possibilities. We have the bromines. So at this point we have the Br2. So you can kind of think back to the mechanism of this reaction. It's going to make this a whole lot simpler. So you can have the Br2 being approaching the alkene from the top. Okay, so this is not an electron movement arrow. It's just saying it's coming in from the top. So that's the one angle, or it can come in from below. Okay, and whether it comes in from above or below is going to have a huge deal in terms of what kind of product you get. So you need to think about both of them. Okay, so for the first scenario, let's say we come in from the top. So we have our Br2 attacking from the top. It doesn't particularly matter in this case, but let's just have it from the top, just to start somewhere. Okay, so if we're attacking from the top, and let's say we're rotating at 90 degrees in this fashion, we'll have the H going backwards, methyl coming forward, so H and Me, and we'll add our stereochemical designations here as well. So we'll have our Me and isopropyl. Okay, so that's one possibility, right? The other possibility is if we attack from the bottom. So if we attack from the bottom, let's do that possibility. If we attack from the bottom, we can potentially also get first bromine over here, second bromine over here. Okay, so in this case, we still have everything in the plane of the board, and we also have these three-dimensional designations. So I'm just going to go ahead and draw them in, and we can fill them in later. And so now let's say if we attack from the bottom, like this, bottom, H is still pointing away from us. Methyl is still pointing towards us. Methyl over here is still pointing away from us. And isopropyl is pointing towards us. So that's pretty easy to actually put together. I can make this methyl group look a little bit nicer by making it come down a little bit. So I'll try to make this look a little bit nicer. So this is the isopropyl. I'm going to have this facing more in a downward direction. Okay, and this methyl group is really kind of facing upward, just to be really rigorous. I'll go ahead and redraw it. Okay. So it's pointing more up. So trying to make this look as tetrahedral as possible. Okay, so now if you look at these, you can go ahead and go through your RNS configuration designation and say BR1, and this is going to be 2, this is going to be 3, this is 4. Thank goodness the lowest priority is facing away from us, so it's pretty easy to say, okay, this is R. Great. Maybe I should go ahead and keep it in the same color just to make everything look nice. Okay, so let's say that this is R. Okay, and from that we can think about priorities on the other carbon. So here, let's go ahead and erase these numberings just to make it clearer. We have the bromine still as priority 1, and here it becomes a little bit more difficult to figure out what the priority is. So we have an isopropyl, so we have to recognize that there's a carbon there. So let's go ahead and redraw this isopropyl group and draw it as if this was the carbon. Okay, so we have carbon, 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 so there's a lot of tie breaking that needs to be done here. So the lowest priority is always, or it's obviously going to be this particular methyl group, because again, this is a CH3. Hydrogen is going to be next on the line no matter which way you cut it, so we're going to have the lowest priority for this methyl group. So this is going to be the lowest priority, so that's 4. So now what we have to do is compare and contrast these two groups. So we have to compare and contrast this isopropyl group right here, and we have to compare and contrast this group over here. Okay, so notice we're not comparing this carbon and this carbon directly, but we're comparing what is attached to those carbons. So if we were to draw this out, we would have this carbon that had CH3, CH3, and a hydrogen, so Me, Me, and a hydrogen. And if we were to go over to the kind of greenish teal looking guy, we would have three different groups attached to it. So we're going to have bromine, methyl, and hydrogen. Okay, and again, this is an easy tiebreaker because we have a bromine, which is a higher priority than a methyl, so this is going to be the higher priority overall. Okay, so let's go back to our original color. This is going to be priority 2, and this is going to be priority 3. Okay. And again, thank goodness, we have our lowest priority group pointing away from us, so it's pretty easy to tell that this is an R. Okay, so now we have an R and an R. So we could beat our heads against the wall and try to figure out what these are by the same methodology. We can do that, definitely. Or you can recognize that these are simply enantiomers of each other. Okay, so I'm going to copy and paste to make that a little bit clearer, hopefully. Okay, so now what I'm going to do is draw that mirror plane that we've talked about so many times. So if we draw our mirror plane, it looks like we have a match. The bromines are facing the same way. Okay, these are facing towards each other. This bromine is facing the same way as this bromine. It's in the plane of the board. This hydrogen is facing away and towards the mirror. This hydrogen is facing away towards the mirror. This methyl is facing towards the mirror, and this methyl is facing towards the mirror and out. So we have a match on the left-hand side. The left-hand side seems like it's an identical mirror image. And if you look on the right, we have the bromines that match. This methyl group is facing away and into the other room, and so is this methyl group. And this isopropyl group is facing away from the mirror and towards you, and just like this isopropyl group is. So what we have is a tie. We have a mirror image. We have an enantiomer. So since we have an enantiomer, what we're going to have is just that simple inversion of our stereochemical designation. So instead of being an R, this is an S, and instead of being an R, this is also an S. So this is going to be an S and an S. So what you get from the Br2 addition is not just one stereochemical product. You get two stereochemical products that are going to be enantiomers of each other. Okay, so that's one thing to take away from that. Okay, so let's move on to the next one. So the next thing we're going to play around with is the HBr addition. So for the HBr addition, this is actually going to be really simple in terms of the regiochemistry. So what we have is our alkene. We have it reacting with HBr. The first thing that you have to be able to recognize is that this is going to go through a carbocation mechanism. Okay, so because it's going through a carbocation mechanism, this is going to end up being a Markovnikov type of addition. So it's going to end up being Markovnikov. Okay, but you always have to keep your mind open for the possibility of some kind of shift, some kind of chemical shift, either an H plus shift or a carbon shift, one of those two. All right, so let's go ahead and figure out where the more stable carbocation is going to be. So we're going to use this double bond as a nucleophile. We're going to end up putting the hydrogen on either the blue or the yellow carbon, and we'll form the more stable carbocation. So let's draw that out. So we're going to either have carbocation on the left, on the blue, or on the right. So I'll go ahead and draw them both out first. Let's say we have the H or the H adding to the blue carbon, and we'll have a plus on the yellow carbon at the end of the day. So isopropyl here, okay, H, second H from the HBr, and then our Me. Okay, so just to make it clear, let's go ahead and I'll make this H right here white to remind you that that's coming from this hydrogen right there. Okay, so that's one possibility. The other possibility is that you can have your carbocation on the left, methyl group right here, and you have methyl isopropyl, okay, and you also have your white hydrogen being added over here. So there's your white hydrogen, which means that you have positive on the left. So we have a tertiary carbocation versus secondary carbocation. Should be extremely intuitive at this point that the secondary carbocation is going to be less stable. So we're going to take this guy and get rid of it. It's not going to happen. Okay, so in terms of the regiochemistry, we have that taken care of. That's easy. So we know where the hydrogen is going to go, and we also know where our bromine is going to go. So bromine is going to end up going here. So the final product is going to look something like this. I'm just going to take this bit right here, this whole section, and what I'm going to do is just simplify it and make it an ethyl group, because that's what it is, just an ethyl group. So let's go ahead and take our original molecule, redraw it. Let's call it an ethyl group, and we'll have methyl right here and isopropyl right here. Okay, carbocation. So now we're going to have some kind of orientation. It's not really clear what's happening here in terms of where everything is. But one thing you can be sure of is that this is going to be a planar molecule. If that's the case, then you're going to have your Br minus either attacking from above or below. So these are the two different possibilities: Br minus from the top or Br minus from below. So these are the two different possibilities. So if you go through possibility A or possibility B, we're going to end up getting two different stereochemical results. So we're going to get possibility A, where Br is coming from above. So say ethyl is in the plane and methyl is facing back, isopropyl is facing forward. And that's a completely arbitrary designation. The important bit is that we actually keep it constant throughout all of this, because whatever orientation this has, it's trigonal planar, so it doesn't really matter too terribly much. So now we'll go through orientation B, and what we'll have is the bromine coming in from below. So bromine from below, ethyl is still in the plane of the board, and then the methyl is still facing away, and the isopropyl is still facing toward you. Okay, and so we're going to get two different stereochemical designations. So we'll get enantiomers, and one of them will be R, one of them will be S. Okay, and you can go through that, figure out R and S, but the important bit is to remember that you have this C plus mechanism, which is going to give you this mixture of stereochemical results. So you're going to get an enantiomer. Okay, so this third sub-question is actually slightly similar. It's actually a little bit, just a tiny little variation of the original question that we did. So instead of doing this bromination in aprotic or non-nucleophilic solvent like DCM, we're actually including a solvent that can act also as a nucleophile. So this is going back to a couple chapters back where we're talking about halohydrin formation. So if you have enough water and if you control the introduction of Br2, you can actually bias the reaction to not give you this dibrominated product. You can actually have one bromine attach, and then the other bromine is preferentially excluded by the water. So the key here is to remember that you're still getting the mechanism of Br2. So one thing you have to remember is that you're still going through this bromonium ion. So bromonium ion is the key. So we're still going through bromonium ion, which means that we can still either attack from the top or attack from below. Okay, so these are the two different possibilities. So let's go ahead and redraw this guy, but just redraw it from the top to the bottom. Okay, so let's go ahead and have bromine coming from the top for the first possibility, and let's think about the actual intermediate for this case. So we have bromine from the top, methyl, and we have isopropyl. And then we also have hydrogen and the methyl. Okay, so same identical bromonium ion mechanism. So I'm just going to move this over to the left a little bit. Let's move this over. And so this is one possibility. And then the second possibility is that we can have the bromine attacking from below. So we can have bromine from below. So we can still have methyl pointing up, isopropyl pointing out, methyl in, isopropyl out. And we'll have hydrogen facing out still, and we're going to have the methyl pointing out. And I screwed that up. It shouldn't be pointing down. It should be pointing up, like that. Not a huge deal, but just to be rigorous. Okay, so these are the two different bromonium ions that you can get. Okay, so here's where things get different. Things are different here once you remember that you're doing the halohydrin formation, in which you actually invoke the water as a nucleophile instead of the Br minus. Okay, so in this case, it actually matters which carbon you end up attacking. So the carbon that you're going to end up attacking is going to be the carbon that is the most stable carbocation-like structure. So here you have, if you thought about this bond breaking versus this bond breaking, you can think about extending this guy a little bit. So it's in the middle of bond breakage. and you're going to have 1, 2, 3. You're going to have a partial positive there. This is a tertiary partial positive. Versus if you did the same thing over here, you would only have a methyl in this other group, so you would have only a partial secondary carbocation. Okay, so of the two, this is going to be the more stable carbocation. So the idea here is that what you've done is you have to imagine this moment in time where one of these bonds is going to be a little bit weaker than the other. And so what you have to do is imagine a moment in time in which one of these bonds is a little bit weaker than the other. So what you can imagine is this bromine bond getting a little bit longer over this way, and this bond getting a little bit less formal. Okay, so this is getting a partial positive instead of a full positive, and the other partial positive is over here. So again, it's a tertiary partial positive instead of a secondary partial positive. So what you have is your water coming in for attack, OH2. So it's going to come in for attack using one of its lone pairs. And at the end of the day, you'll have water attacking this carbon on the right and not the one on the left. Okay? So the result from that is going to be this guy over here, where you have your bromine on top, like this, hydrogen still facing away, methyl still facing towards. But now you have your water coming in from below. And obviously the mechanism is a little bit more complicated than this, but we're not really worrying about the complete mechanism, so I'm just going to abbreviate it by saying at some point this OH2 loses another hydrogen as H+. Okay, and at the end of the day we get this halohydrogen. So we can orient the rest of the molecule very easily. Methyl still facing back, and the isopropyl is facing towards you. Okay, and that's the result from this first orientation. So again, you have to remember that for the halohydrogen formation, you're going to be proceeding under a slightly anti-Markovnikov addition in terms of how this water adds. But then after that, you also have to remember that the stereochemistry is going to be influenced by the bromonium ion bit. So because of that, you're going to have an anti-addition for stereochemistry. Okay, so this is the one possibility. And then from there, we really only have one other possibility in that we do the same thing, but we're doing it with this yellow. So what we're going to have is this same comparison between which partial carbocation is going to be more stable. And in that case, it's going to be the same side. So it's going to be more partially carbocation-like. And this is going to be, okay, get rid of this, partial positive. It's more of a tertiary. Okay, so what we'll have is the water, same thing, come in for addition from above this time, not from below. Okay, and so the result for this case is that we're going to have, after we lose hydronium, we're going to end up having the first Br that was used to form the bromonium, that's going to be facing down. We're going to have our carbon-carbon bond, and we're going to have our water facing up like this. But obviously this is after we've lost the other H plus from the water. Okay, and so then also we're going to just have to fill in now the methyl and hydrogen. Hydrogen still going back, methyl is still coming forward, and this methyl and the isopropyl, this methyl is still going back, and this isopropyl is still coming forward. Okay, and after we do that, we're pretty much done. So we have two different outcomes here. We have one stereochemical product down below and one stereochemical product up above. So it looks like this, let's go ahead and add in our RNS. So this bromine is going to be 1, 2, 3, so this is going to be R. And it looks like our lowest priority on the right is still facing away from us. So just like before, we're going to have the isopropyl and the methyl and the OH. So it actually looks like this blue right here is very similar to this original right here. So we have R on the left, and we're still going to have R on the right. In this case, the OH is still the highest priority, just like the bromine was up above. And if we look over here, we're going to have the same kind of situation with the yellow as we did with the blue. So bromine, methyl hydrogen, bromine, methyl hydrogen. So this is still going to be S. So we're going to have an S right here, and the OH is still up above, and so OH isopropyl methyl and Br isopropyl methyl. Okay, so we're going to have two different, or the same actually, stereochemical designation here. Okay, so in this case, it actually worked out really well that we have the same two stereochemical results as we did for the Br2 addition. So we had an RRSS for the Br2, and in this case we still got an SS and an RR. And it just so happened to be that way just because of the fact that we know that this type of halohydrin formation is going to occur in a semi-Markovnikov way. So if there was no stereochemical control, which may happen for some things, we could have potentially had the water attack the left and not the right, or the left and the right. But because this is anti-Markovnikov, it actually works out just the same. Okay, and so these are going to be the two products for the halohydrin formation: the yellow up top and the blue F2 down below. So these are the only two products that we should really get, and they are enantiomers.